specified values are, then you're okay. You've done a good enough approximation for design purposes. At that point, you can walk over to your circuit simulator and get the actual DC operating point. But for design purposes, close enough is usually good. All right, so let's do some diode stuff here. I'm not sure if I had a diode question prepared. Do you want to talk about the one on the previous final? Because I know some people were concerned about that. We did it in class already. I don't want to waste your time with something that you've already seen.
We did it in class.
We did it? Yeah, we did do it in class. Yeah. You okay? All right. Generally, okay, so if I just have a diode connected up to a voltage source, so here I connect it up to some very specific voltage, and there's no other resistances here, I really then care about this, I really then care about that exponential relationship, right? Then I really care that ID equals ISE to the 40 CD. That's my approximation equation, right? If I have a direct voltage directly applied to that diode, then I really care. Because I'm able, not a lot, that's just barely over 1 milliamp, right? So by putting a resistor in front of here, that's why as designers, now we don't necessarily have to go to the exponential equation. We only have to go to that equation when we are directly controlling the voltage directly on the diode. Okay? Or if we want to know exactly what the voltage across that diode is. In a case like this, what you can do is you can just say, here's 5 volts, and this is just like what we were doing for the BJT when we forward bias it. There's 4.3K. I'm just going to assume that the diode is 0.7 volts. So I say plus minus 0.7 volts. That means that the current going through here is going to be 1 milliamp. So that's 4.3 volts. So 5 minus 0.7 divided by 4.3K gives me 1 milliamp of current. Now it's relatively insensitive to that diode. That diode voltage will change a little bit, and it's really not going to change that current drastically because the current is now determined more by the resistance than it is by the diode. So in the cases that we're looking at here, where we're talking about biasing a diode or biasing a BJT, it's the resistors outside of the nonlinear component that make our life easier, because now we're putting the burden on the resistors instead of the burden on this exponential equation. We're now switching over to a linear Ohm's law to determine the current through that diode as opposed to that diode equation. Now, here's what I would do. I would say, okay, I'm assuming this is 0.7 volts. I got 1 milliamp coming through. Is my manufacturer specified value approximately 0.7 volts? So they'll specify a value, right? They'll say the diode was tested at VD equals 0.7 volts, and at ID equals, so given an exact voltage of 0.7 volts, we got a diode voltage of something, right? And they're going to tell you what that is. If that's approximately 1 milliamp, good enough. Okay? If that's what you came up with, and it's approximately equal to that, great. If it's way off, if you get 100 amps going through this thing, but they tested it, and it was only supposed to be 1 milliamp, okay, now you're going to have to go through that iterative procedure. You're going to have to make a better guess of what that voltage across the diode is. Right? So you have to think intelligently here. Assume that the burden is going to be on that resistor and that you can just put 0.7 volts there. Look at the manufacturer specified value. I'd say if this is approximately 1 milliamp or whatever you came up with. If it's approximately whatever you came up with, then you're okay. Just proceed on to whatever the second part of the question is. So for diodes, for BJTs, just bias it at 0.7 volts and go. Unless it specifically says use an iterative method to find the exact DC operating point, which I think would be a poor use of testing your knowledge of this course. I'll leave it at that. Okay, now let's see. I got to make up a question that's not too similar to the question that I made up for you already. Does anybody have a specific diode question that they want to look at? The one at the final, yeah.
Similar to just change the number. Change the value. This year's final. Change values. Add every value by 1.
Okay, let's make up one. We'll make up one where we can find the DC operating point, and then we'll make up one where we can do small single word thing. So you just gave me an idea for one, so let's just make it up here. Here's 10 volts. Here is. So I want to do So we'll do one diode. They're identical diodes, okay? Let me just change this a bit. I want to put a resistor here. I'm trying to think of something that actually makes sense here. Okay, I think this will work. Let's call this 1K and this one 2K. So how would I solve this? And the question would be something like, what's the current through here? What is I1? So here's what you do. In all these questions, like I was saying, same for BJT, same for this, you always just assume that it's forward biased and that it's 0.7 volts, okay? So right away, I'm going to assume here that this one is 0.7 volts, right? So that means that this node here is 0.7 volts. Then this diode, I'm going to assume is forward biased, which makes sense because we've got a pretty high voltage here. So we should have enough voltage for 0.7 here and 0.7 here. I'm going to assume that this one is forward biased at 0.7 volts. So what does that tell me? That tells me that this node voltage up here must be 0.7 plus 0.7 is 1.4 volts. And that's completely sufficient to specify the problem here. So we could say, what's the current going through that resistor? I could say 10 volts minus 1.4 volts divided by 1K equals, I guess that'd be 8.6 milliamps.
Yeah, that's so easy.
Right? And then, part 2 of the question could be something along the lines of, what's the current through this diode here? Let's call this here IT1. What's the current through that diode? Well, I know that the current through this diode plus the current through here must equal 8.6 milliamps, right? It has to equal, the current has to go through those two branches. So what I could say is the easy target here is the 2K. So what I would say is that there's a 0.7 volt drop across this 2K resistor. So I'd say 0.7 volts divided by 2K plus that other current, ID1, must equal 8.6 milliamps. And then somebody with a calculator could solve ID1 in milliamps. Anyway, doesn't matter. It equals some number. Some number. So watch what I did there. I just assumed that there's a 0.7 volt drop across that diode. 8.25 milliamps. Okay. 8.25 milliamps. No, that doesn't sound right. Yeah, that doesn't sound right at all. Oh, is it? Okay, so that's right. So what I would do then is I would check, because this seems a little bit high, I would check, is this approximately close to the manufacturer specified value? I'd say if it's within a factor of 10, a factor of 5 would probably be okay. A factor of 5 might be better. Then good enough. We don't need to make any corrections. I'd say at that point stop. And so on an exam, it would be foolish as somebody who needs to give you enough time to finish the exam to make a question overly complicated, right? We need you to be able to do A, then B, then C, then D, and move on to the next question. The goal not being to make you run out of time. So there's an example of a DC analysis. I just assume that things are forward biased. Now, if you see something that's obviously wrong, like here, let's say that this diode was facing the other way. What I would do is I would say, okay, yes, this one's going to be forward biased because we have positive voltage and ground, so current's going to want to go through this way. Current's